Welcome everyone to the Foundry by Forge College. I'm absolutely thrilled you're joining us today for another explainer. So if you were with us for our last lesson, Legal and Institutional Timestamping, you know we explored how courts and institutions rely on certified time to resolve disputes. Well, today, as part of our journey through history before blockchain, we're taking a trip deep into the actual mechanics of history itself. We're going to bridge the gap from those legal theories directly into how organizations practically engineered record systems to sustain institutional trust. Basically, we're looking at how they built systems to make absolutely sure the past stays exactly where it belongs, in the past, entirely unaltered.
To kick things off, I want you to imagine stepping into the shoes of a forensic investigator for a second. Imagine someone hands you an archive. Let's say it's a corporate minute book or maybe a digital property ledger from 10 years ago, and they ask you a very simple but kind of terrifying question. How do you prove history hasn't been rewritten? How do you know for sure that a rogue employee or a sneaky hacker hasn't gone back in time, altered a crucial sentence, and just covered their tracks? It's a fantastic puzzle, really, and looking for that tampered evidence is the exact problem historical record keepers had to solve long before modern databases even existed.
Okay, let's dive into this. Here is our forensic investigator's roadmap for today. We're going to go from theory to practice, build a digital chain, see trust anchors in action, run through the forensic checklist, talk about preserving records over time, and finally, prepare for blockchain.
Let's start with Section 1, from theory to practice.
We're moving from the abstract legal concepts of our last lesson straight into physical reality. Because, it's one thing for a lawyer to say a record is legally certified, but it's another entirely for an engineer to design a system that practically guarantees its integrity. We need a mechanism that makes tampering blindingly obvious, and that brings us to our first major tool, deterministic hashing. You can think of this computational process acting just like a digital tamper evidence seal. Imagine buying a bottle of medicine at the pharmacy. It always has that tight plastic shrink-wrap seal around the cap, right? If someone messes with the contents, that seal is visibly broken, and you instantly know not to trust it. Well, deterministic hashing does exactly that to digital data. You feed your document's bytes into a mathematical function, and it spits out a unique, fixed-length string of characters called a digest. The absolute magic here is the deterministic part. If you change even a single comma in the original document, the output digest changes completely. The seal is shattered.
Moving right along to Section 2, building a digital chain.
Now, we aren't just sealing one isolated document here. We're linking them together to lock history in place. The logic behind this is like a minimalist engineering blueprint. To build this chain in a program like Python, you'd follow 4 precise steps. First, you hash the payload content, which is your actual data. Second, you add a precise UTC timestamp, permanently locking it to a specific moment in time. Third, and this is the genius part, you link the previous entry's hash directly into this new entry. Finally, you output a serialized entry hash for the whole block. Each block perfectly locks into the next, exactly like physical links in a steel chain. If someone wants to secretly change record number 2, they have to break and recalculate record 3, 4, 5, and so on. It makes tampering computationally exhausting.
When we look under the hood at the JSON blueprint for these components, we see 4 essential fields holding this whole machinery together. First up, the timestamp. This is the exact machine-readable moment the record was created. Then we have the payload hash, which is that deterministic digest of the data we just talked about. Next is the previous hash, serving as that unbreakable chain pointer reaching back into the past. And finally, the issuer. This is our trust anchor, which might be a notary or maybe a secure server. I do want to point out an absolutely critical engineering detail here. Stability is everything. Stabilizing the serialization simply means keeping the exact order of these fields the same every single time. If your computer randomly scrambles the order of the fields before hashing them, your tamper-evident seals will look broken even when the data itself is perfectly fine.
Let's move to Section 3, trust anchors in action.
Let's see how all this builds into real-world scenarios, where sneaky actors might actually try to alter history. Different organizations handle these mechanics in the wild in some pretty clever ways. Think about the context. What if someone tries to backdate a land deed at a land registry? Well, they rely on local registry stamps and notaries as their trust anchors, and investigators will physically compare ledgers and verify seal impressions. Or what about in scientific data, where precision is literally everything? They use network time protocol servers that are synced up to atomic clocks, and they verify things by recomputing checksums. If a rogue secretary tries to alter corporate minutes, the trust anchor is a signed minute packet kept locked in a physical safe, and the forensic method is validating the chain digest of the scanned pages. So different industries, completely different anchors, but exactly the same mechanical goal, preventing history from being rewritten.
So we can essentially boil all of this down to one simple fundamental equation for historical record keeping. Trust plus survival plus verification equals provenance. You have to balance what is authoritative, your trust anchor, with what can actually survive physically over time. And finally, how an examiner can mechanically test that integrity. You really need all three functioning perfectly to know the true origin and history of any record.
Which brings us to Section 4, the forensic checklist.
Because having a brilliantly secure system is totally useless if you don't know how to audit it when the pressure is really on. Let's look at what happens when a forensic script goes to work. In a valid chain, the entry hash matches the data perfectly, and the previous hash matches the prior entry. Everything hums along beautifully. But in a tampered chain, oh, this is extremely satisfying. Imagine our bad guys sweating in a swivel chair as they try to slip a forged document into the archive undetected. Our simple script recomputes the hash, and bam, hash mismatch error. The chain pointer throws a mismatch. The bad guy is caught red-handed by simple, unfeeling math. It is a beautiful thing to witness.
So the verification protocol itself relies on a rigid set of mechanical steps. First, you recompute the payload checksums yourself to catch any tampering. Second, you confirm the previous hash matches the recorded predecessor exactly. Third, you check external attestations, things like notary stamps or third-party time proofs. And finally, you review archival logs for format migrations. By the way, practicing these exact concepts and running these audits through the different educational programs we offer at Forge College is a fantastic way to build a rock-solid foundation in digital forensics. This mechanical verification is exactly how professional audit teams reconstruct disputed history today.
Section 5, preserving records over time.
Now we have to discuss the ultimate enemy of any archive, time itself. How do records survive not just for a few years, but for decades or even centuries? Well, the answer is redundancy plus migration planning. Defeating the decay of data over decades requires a very active plan. Deterministic hashing is incredibly powerful, but if the hard drive rots or the server room catches fire, all those beautiful cryptographic hashes are gone forever. Poof. Without offsite backups, microfiche copies, and meticulously documented format migrations, like moving from old floppy disks to modern cloud storage, provenance is eventually lost. You have to actively fight data decay because time destroys absolutely everything that isn't backed up.
And finally, Section 6, preparing for blockchain.
Now that we have our forensic notebook completely filled out, let's look at how all this history tees up our destination in the Web3 space. When we look at the ancestors of Web3, they're all right here. Objective digests, which we know as payload hashes, chained pointers, which give us our linked history, and public external attestations, which serve as our trust anchors. The incredible realization here is that blockchain didn't actually invent these concepts out of thin air. Not at all. It simply took these historical, mechanical building blocks, the exact same ones used for decades in corporate safes and scientific logs, and placed them into a totally new, decentralized architectural design.
Which leaves us with one final, very provocative question. What happens to the chain when we remove centralized trust anchors entirely? What happens when there is no notary, no corporate secretary, and no central time server to rely on? Well, that is the exact puzzle that blockchain solves, and it is the core focus of our Blockchain Fundamentals track. To continue your journey into Web3 and explore the answers to that question, make sure to visit our website at forge.college. It is absolutely packed with educational resources to help you master these exact subjects. Thank you so much for joining me today for this explainer from the Foundry by Forge College. Keep learning, keep verifying, and I'll see you in the next one.